Hi all. Now we are going to discuss on AC voltage controllers. So the basic function of AC voltage controllers is to convert fixed alternating voltage to variable alternating voltage without change in frequency. So the basic example what you can consider is nothing but an auto transformer. So you are able to regulate the output voltage without change in frequency by using an auto transformer, or it can be done using a tap changing transformers. So it is basically used in AC drives, it is used in lighting control, then it is also used for motor starting and auto transformer starting you can just think about. And with the advent of technology, with the new devices which being introduced, then these auto transformers and tap changing transformers are not commonly used nowadays. So they are being replaced by thyristors and triac as an AC voltage controller. The basic example again you can take here is nothing but a fan regulator. Here basically you are trying to control the output voltage from the regulator which is given to a ceiling fan. And the advantage of thyristor based or track based are high efficiency, flexibility in control, compact size and less maintenance. You can just think about the size of a regulator, how compact it is, how flexible it is to control. But one of the main disadvantages with the use of these powertronic devices is that it is the introduction of the harmonics in the system. So now we will just see the basic type of half-wave AC voltage controller. So this is the circuit diagram. You have your source voltage Vm sin omega t. Then you are connecting one thyristor and one diode in anti-parallel, and which is connected to a resistive load. So the current direction is like this, it is flowing. So you can see that this is your input supply voltage. From 0 to pi, the thyristor T1 is forward biased and the diode D1 is reverse biased. So therefore, thyristor you can control the phase angle at which it starts to conduct. So during the positive half cycle, I am going to fire my thyristor at an angle alpha. So therefore, till angle alpha, the output voltage is 0. So that is visible from here, the output voltage is 0. And once the thyristor starts conducting, then the input voltage will be appearing across the load through the thyristor from 0 to pi. At angle pi, what happens? Thyristor T1 is reverse biased, and since the resistive load, the current will be flowing following the same sequence of your voltage. So current has also reached to 0, therefore thyristor T1 is commutated. Now at pi, diode D1 is already forward biased and therefore it starts conducting. So therefore whatever be the input voltage, that will be appearing across the load. So here you will be getting your output voltage like this, and the current will also be following the same way in which the input voltage is, because it is Vm by R is a resistive load. Angle between the current and the voltage both are the same. And again the next set of at 2 pi plus alpha, thyristor T1 is again forward biased and triggered at angle alpha, so the output voltage again comes. So this is how a basic single phase half-wave AC voltage controller works. But the main disadvantage with a half-wave AC voltage controller is that a DC component is introduced in the supply and the load circuits, because the positive half cycles are only controlled and the negative half cycles are not controlled. So in order to avoid that, we will be going with a full wave AC voltage controller rather than going with a half wave AC voltage controller. So this is a full wave AC voltage controller. So now that diode is again replaced by the thyristor. So now you are having two devices, T1 and T2, which are connected in anti-parallel, connected to the resistance. And now alpha is the angle at which you are going to fire thyristor T1, and again alpha is the angle at which I am going to fire thyristor T2. So The waveforms at both the half cycles are symmetrical in nature. And again, this is a resistive load. Therefore, the current will also be following the same nature of your voltage. So this is the output voltage. Again it goes. So this is the one which we normally use, a single phase full wave AC voltage controller. Now we will be discussing on the basic control methods used in the case of an AC voltage controller. The first one is the phase control and second one is the integral cycle control. Phase control is whatever we have already discussed. You are controlling the output voltage by controlling the phase angle at which you are firing your thyristor, here and also here. So basically what happens is that the output voltage, we already discussed that in AC voltage controller is basically trying to control the fixed alternating voltage to a variable alternating voltage. So depending upon the firing at which you are going to fire the thyristor, the average output voltage is changing. So this is shaded area will be changing depending upon the angle at which you are firing your thyristor. Next is integral cycle control. So integral cycle control is using this particular technology. So this is the input supply voltage Vs. Now we can observe that it is continuously, it is producing throughout the period from period. So now what you're trying to do is that you have two thyristors T1 and T2, and these thyristors are being fired at angle 0 itself. That is, the firing angle is taken as 0 itself. That is visible from here. You're going to fire the thyristor at omega t equal to reference as 0. So therefore, whatever be the input voltage, it will be appearing across the load. And after some point of time, what you are going to do is that you are turning off both T1 and T2. That is, T1 and T2 is kept on for a longer period of time. So during that time, the output voltage is 0. Or else you can say that firing pulses to the thyristors are being taken away for a certain period of time. And after that period of time is over, again thyristor T1 and T2 are being fired, and the output voltage will be appearing across the load. So what happens is that for a certain period of time, the voltage applied to the load is made 0. So with that, you are able to control the load under question. So that is with the case of an integral cycle control. Next we are going to discuss the single phase full wave AC voltage controller with resistive load. We will see in detail. So basically there are 4 configurations are there in order to achieve this AC voltage controller. So the first one is 2 thyristors kept back to back, and which is being triggered from a single source like this. And then you can also use a triac, which is again a bidirectional conducting device, or else you can choose this particular scheme. But we will be discussing our explanation with the case of the thyristors which are connected in anti-parallel. So this is a basic circuit. Vt1 is nothing but the voltage across thyristor T1, Vt2 is nothing but the voltage across thyristor T2, and this is source voltage and source current and the load current. Now here in this case, the load current and the source current both will be the same because the conduction will be happening only through here. So Is and I0 are the same. And this is the resistive load, so therefore the output voltage V0 and I0 are in phase with each other, and the magnitude will be I0 is equal to V0 by R. So during the positive half cycle from 0 to pi, thyristor T1 is forward biased, and now I am going to trigger the thyristor T1 by giving the gate current at an angle alpha. So therefore the output voltage will be occurring like this. Then during the negative half cycle from pi to 2 pi, thyristor T2 is forward biased, and I am going to fire the thyristor at an angle alpha of pi plus alpha, and the output voltage will be appearing across the load like this. And that sequence is going to continue. And since the I0 is nothing but V0 by R, so it will be following the same nature of your voltage V0, and the source current is also the same. Now we need to draw the voltage across the thyristor T1. So this is the period during which thyristor T1 is conducting. So when the thyristor is conducting, the voltage across the device is nothing but a positive voltage across the device, and that is from alpha to pi. So during the time 0 to alpha, none of the thyristors are conducting, and therefore whatever be the source voltage will be appearing across the thyristor T1. And from alpha pi to pi plus alpha, again none of the thyristors are conducting, and therefore this negative voltage will be appearing across the thyristor, which is nothing but the source voltage. And after that, you just need to observe it here. From pi plus alpha to 2 pi, thyristor T2 is conducting. Thyristor T2 is conducting from pi plus alpha to 2 pi. That means there will be a voltage drop across the thyristor T2 during the conducting state. Let's say it is 0.7 volt. So this 0.7 volt will be appearing across the thyristor T1 as minus 0.7 volt. So that is why this is drawn at the negative side with respect to the reference line. So during that time, this voltage will be plus 0.7 voltage. So the same thing is happening over here. That is, whatever the voltage drop occurring across the thyristor T1, it was 0.7 volt when it was in conducting state. So that voltage is appearing across the thyristor T2 as a negative voltage over here. So you just need to observe the voltages which is coming across the thyristors T1 and T2, because they are connected in an anti-parallel. Whatever the voltage drop across this device will be coming across the other device with a opposite polarity. Now we need to find out the average output voltage. You can just observe from this output voltage, the average output voltage will be 0 because both the sides are identical in nature. But we can derive the RMS output voltage. So V naught RMS is equal to 1 by pi integral alpha to pi Vm square sin square omega t d omega t. So all under the root. So this can be used to derive the RMS value of your output voltage. And why we have taken this 1 by pi is because basically you are trying to square of the RMS value. So basically you are squaring it. So the waveform will be like this. And again here also if you are squaring it, it will be like this. So basically the RMS voltage waveform will be having a time period of pi. But the average output voltage is 0. Now we should also consider the harmonics of the output quantities, and for that we will be using the Fourier series analysis. We will be deriving the A0, AN and BN in order to find out the harmonic components, and with that we will be deriving the power factor and the average power which is delivered to the load. So that derivation will be shared as a note along with you. Thank you.